Hello everyone. Today I'm Hardi Desai. I'm going to present you my project at SAS, which involves around the physical distancing and the crowd density monitoring using computer vision. So the motivation behind this project was the with COVID-19, it was very important to monitor the physical distancing in closed environments. Given the COVID-19 situation, we wanted to build a solution which is non-invasive and anonymized. Our target areas included spaces such as cafes, plant floor production line, retail checkout, and airport security. All these places already have security camera in place. So the idea was to have a system build or a solution build which can easily be embedded using the security camera, and we don't need any specialized kind of a hardware or software. Here, as you could see, I have a screenshot from the SAS cafeteria in our building. We have geofenced the area into 4 locations. We have the entrance, the cashier section, the salad bar, which is at the top right, and the dessert area, which is at the bottom right. On the right hand side, we could see our analysis where we are detecting the number of individuals, and also we are kind of figuring out the number of clusters which are formed based on the physical distancing norm. Here we have taken the social distancing parameter as 6 feet. Also, we have a small analysis of number of people in each of the areas we have selected. Moving forward, our solution consists of 3 important components. It is basically we are using the SAS deep learning capabilities along with the event stream processing capabilities. First, we have the computer vision based algorithms mainly developed using deep learning capabilities in SAS, which which detects the individuals, tracks them, and also we have some post facto analysis which helps us calculate the distance between employees or the individuals whom we are tracking, and also the time of interactions. Next comes the visualization and reporting. In visualization and reporting, we have developed heat maps which can serve as a guidance to the cleaning crew. We also have the analysis of the violations and the summary of all the violations in the SAS Visual Analytics or VA. Lastly, using the ESP capabilities or the event stream processing, we do a real-time monitoring of the situation, which helps us provide real-time alerts as an email or a text notification along with the hotspot identification. Now, I would be discussing the computer vision pipeline, which has helped build us the solution. Starting, we get the images from the CCTV camera, which is already present as a security footage. Next, we resize the images to the size of 416 x 416. Once we have resized, it is important for us to label or get the training data for our deep learning models. In order to reduce the labeling efforts, we have used the state-of-the-art Detectron architecture, which is an open source algorithm to score and find out the number of individuals. These architectures are trained on pre-trained models with huge data sets, and class like a person is easily available. We have manually spent time to refine the annotations because even these algorithms are not 100% correct. Another important aspect to know here is these are heavy models, so they have a large number of parameters, and also their inference time is not in real time, like it takes a while to infer. So we cannot actually use them in an edge device. Hence, we train a tiny YOLO V2 model in DLPy, which is using the SAS capabilities. I would like to reiterate here the reason we use the tiny YOLO version 2 architecture for training the object detection algorithm is because the tiny YOLO model is smaller in size, hence the inference time is less. Also, the memory footprint is less. Once we have detected the individuals using the tiny YOLO model, we use a person tracking algorithm which is embedded in the event stream processing. A very important aspect here, since we want to calculate the distances between the individuals, we do the perspective transform, which I'll be shortly discussing in the next slide. We calculate the distance using the perspective transform. And lastly, we have the clustering, visualization, and the visual analytics report, which provides a summary of all the violations. Now, coming to the perspective transform, it is important to generate the top-down or the bird's view of an image. This is because the camera angle at which the security camera, which is at the top, it's not at that imaging plane, and objects which are farther tend to shrink. Due to that, we need to correct the camera angle. As you could see here, the image on the left, we have a weird camera angle, but using the perspective transform, we are easily able to calculate the top down, easily able to see the top down view. And now we can map the pixel distances to the true world distances. Our solution is in combined effort of the SAS IoT team as well as the computer vision team. We have an on-prem edge device which in real time collects the video footages from the camera, and using the SAS ESP we can do the real-time analysis. ESP also has the capability to have real-time email as well as text notification. We also have a real-time dashboard. On the cloud, we have used deep learning capabilities of SAS to conduct the person detection as well as tracking. And we also have a post facto interactive dashboard built in SAS Visual Analytics or VA. Let me now discuss the IoT dashboard which was used for real-time monitoring. As we see here in the IoT dashboard, we can see the live camera footage, the annotations of the individuals who are very near. We also have the total number of alerts, the alert trend, and what were the recent notifications. Now, moving forward to the next page on this dashboard, we have an analysis of all the alerts which were generated, and these could be filtered on the date. Lastly, we have the option to manage the cameras, and more importantly, the individual has an option to select what is the distance threshold or at what distance should the violation be ticked in. Again, the distance, the interaction time, everything it can be monitored by the individual. I would now like to discuss the visual analytics report. The visual analytics report, as you could see here, we like no two interactions are same, and what kind of an interaction could be qualified as an violation is keeps on changing country by country. Like US advises about a 2 feet, 6 feet of distance. However, UK advises about 2 meters. So there is still certain difference. Given that, we wanted to give the user the capability to decide what would be the physical distance parameter as well as the interaction time parameter. Our reports can be sorted by the day of the week. And as you could see, depending on the day of the week, the violation percent, the severity, and the average violation time also changes. We further can drill down based on the location, whether it's the salad bar, entrance, dessert, or cashier. And we also have the person interaction plot. No two interactions are same. If an interaction which was where two individuals were at a distance of say 12 feet and they were maintaining like they just interacted for a few seconds, then they have a lesser probability to come across get the COVID. However, if the person is at a lesser distance and is interacting for more time, those kind of interactions are more severe, as we could see in the person interaction plot. Also, the individual or the user has the capability to select what the severity parameters should be. All this could be drilled down also based on the location. So here, as we see, an individual can select the severity level based on the quadrants. The lower right quadrant, which is the least severe, here we have kept at a lesser value, and the upper left corner quadrant, which has much higher severity, we have kept it at 1. So as we could see, the severity plot, the violation of the person keeps on changing based on location. Coming to the details tab, we have 3 different charts here. The first chart is the customer arrival and the violation percentage based on the day of the week. As we could see, we have a positive correlation between the number of individuals or the customer arrival and the violation percent. Next, we could drill down on the day of the week on the location based analysis. The tree chart on the top right provides us couple of information based on the location. The size of each of those sections provides the number of individual, while the color provides how high was the violation percent. Red indicates that there was too much violation. However, green indicates the violation percent in the particular location was lesser. Lastly, we have the time-based analysis in the bottom, where we have aggregated the data for 15 minutes interval. As we could see, I have narrowed down on Thursday with cashier location for the time-based analysis. Clearly, we could see a positive trend here. Probably at the cashier section, we had less individuals during 12:15 to 12:30 time, and hence the violation percent was lesser. But as time went by, the violation percent increased as more and more individuals came by at the cashier section. A key part to be noted here that all this analysis has been done using the pre-COVID data. Next, we have the hotspot analysis. Till now, we were trying to focus on about the interactions about each of the individuals. However, it is also important to know at which location the physical distancing norms were failed just due to the intrinsic nature of the objects which are present. And we have aggregated it over 5-minute interval, and we are also this could provide a guidance to the cleaning crew where they should be focusing to clean the areas. Also, it can provide whether we need to change the environment in any form so that the physical distancing norms which are guided by the CDC could be followed. Lastly, I would also like to let you all know that we have published a paper in the IIC Journal of Innovation titled The Physical Distancing and Crowd Density Monitoring Using Computer Vision, which can be found at the link. Now, moving forward, as we all are getting vaccinated, this analytics is not just limited to this use case. The kind of analytics we did in this project could be applied to various industries, and the current examples what I discuss here, it's not an exhaustive list. This could be used in retail or manufacturing retail for intelligent recommendation based on how many cashiers do you need to be there in a supermarket at any given point of time. Because using this analytics, we can probably know that what was the crowd when there was more crowd, and there could be an entire optimization on the number of cashiers. Similarly, in the healthcare industry, the hotspot analysis, which we did for this use case, could be used for smart cleaning. In businesses, it could be used to understand the real time count of individuals who are coming to the office, how many people are there, and etc. Also, in manufacturing, the way we have geofenced the different areas in this project, we could be probably monitoring the restricted zones in a manufacturing company and even provide a real-time alert if we see any individual in a zone where they should not be. I would also like to thank the entire team who has helped me build this solution. This was a combined effort from our team as well as the IoT division. So, thank you all.